My apologies for the slightly longer than usual delay, but we're back, as promised, with what's called conjugate addition. We're going to reintroduce our concepts of kinetic and thermodynamic control. These species here can be generated using Aldol condensation reactions, where there's a double bond between the alpha and beta positions of an aldehyde or a ketone. Our normal nucleophilic attack we've seen until now has the nucleophiles attacking the carbonyl for obvious reasons. An anionic nucleophile is very attracted to the very positive carbon that draws it in, and we make a sigma bond there. We didn't give it this name before, but we could have called it a 1,2 addition. The name derives from the mechanism. The nucleophile, where it attacks, is called position 1. And then where the electrons flow to is the second number. And that they didn't travel past the atom that's one away from 1 away from 1 being 2. So 1,2 addition we saw with things like organolithiums and Grignard reagents. So that is nothing new. And so those were strong nucleophiles, and they were the worst possible leaving groups we can think of. Think about methyl minus, conjugate base of methane, the weakest acid we know. Means methyl minus is the worst leaving group we know. So that was a one-way story. The leaving group couldn't leave, so we were stuck with this result, and we protonated it, and we made an alcohol. So that was what we saw in chapters 15 and 16. Still useful reaction. But now we have a new kind of nucleophile that you don't even know about yet, but it's a good nucleophile, but it's also a good leaving group, which means it's the conjugate base of an acid with a pKa of less than 12. Look back in the notes from the start of the semester when we reviewed leaving groups. Let's look at these nucleophiles down here. Jump ahead a little bit. If the nucleophile is also a good leaving group, ammonia is the conjugate base of the ammonium ion, which has a pKa of 10. That means ammonia is a good leaving group, as are the other amines. Enamines, same story, except their nucleophile position is over here, as we just saw. They will be attacking at this position because the lone pair resonates in, and then they attack. This, which we made during Claisen condensations, before we put the proton on it, we had an anion of a carbon that had, when it had its H, was a pKa of 10. That means this is a good leaving group. It's also a good nucleophile. So these are all good nucleophiles for conjugate addition, and it's got a funny name down here, which I'll explain shortly when we look at the mechanism. So if your nucleophile is also a good leaving group, that means the attack here is reversible. You can attack, and because it's able to leave, it can leave. So it's going back and forth, back and forth. That's equilibrium, right? This was a one-way street because the nucleophile was too poor of a leaving group. But any of these nucleophiles can have this go backwards. So what happens in reality is this 1,2 reaction happens maybe 10,000 times. And then the 10,001st time, the nucleophile sees, oh, there's also an attraction down here. It's not as strong. If you do a resonance form of this where the electrons resonated up to O minus, you'd have a cation down here. It's not a happy cation, but it's a contributing resonance form, which means there's some cationic nature to this carbon. So maybe 1 out of 10,001 times the nucleophile attacks there. And when it does so, the electrons flow all the way up to the oxygen, because oxygen does that. It pulls electrons, right? So let's follow the rules here. We attacked here, electrons entered here, 1, 2. We're attacking here, you call that 1. They flowed all the way past 2 and 3, all the way up to 4. We call it a 1,4 addition. It's called a conjugate addition because resonance was involved in the middle here. Conjugation is synonymous with resonance. And this is an enolate. Hey, enolates sure belong in this chapter, don't they? And the enolate is the conjugate base of an aldehyde in this case. And because our nucleophile is one of these, and it's not a terribly strong base, we're not restricted to solvents that like Grignards and organolithiums were here. Our solvent can have a proton. And that's a good thing. Like an alcohol solvent could protonate my enolate here, and it won't destroy my nucleophile. Remember, that was the problem with organolithiums and Grignards. If you mix them with alcohols, they got destroyed in an acid-base reaction. That is not an issue here, but at the end, the alcohol provides a proton that can protonate the alpha position. So now what we're going to do is ask ourselves, when equilibrium is allowed to happen, which of the two products is going to be favored? The 1,2 or the 1,4? And the answer is, if equilibrium is allowed to happen, a pi bond between carbon and oxygen, which is the weakest link in this molecule, is more stable than the pi bond between carbon and carbon in this molecule. That's a more stable pi because oxygen's more electronegative. The 1,4 product will predominate. So we need a combination of one of these good nucleophiles that's also a good leaving group. We need to have some kind of pi bond on the carbon that's alpha to the beta position. And then these nucleophiles will attack the beta position and generate this kind of 1,4 product instead of a 1,2 product. Mechanism down here for a couple more. Here's this anion right here. Well, if these are both methyl groups, then this anion would attack here, resonate up to the 4th atom away. 1, 2, 3, 4. It's called 1,4 addition. Enolate protonates, and you make this lovely product here with a new carbon-carbon bond there. Similarly, if I use a species like this one with a nitro group up here, that's a group we haven't seen before. We're going to see it more and more as we get to test 3. So let's just have a little preview. It's the most electron withdrawing group we know, even more so than a fluorine atom. So it really pulls electrons, and this is one of the nucleophiles here. It's this one. It'll do a 1,4 addition. Electrons flowing all the way up to this O-, resonate back to pick up a proton from the ethanol, and you get this species here. Similarly, this is much like this one over here, a nitrile. It's got an extra methyl on this carbon. It doesn't change things. Gilmans are on my list here. Okay, we got to remember Gilmans, if given a choice, well, we know they don't do 1,2 addition. We said so way back in chapter 15. Gilman won't do what an organolithium does. A Gilman won't do what a Grignard does. Here, it has a choice of adding 1,4 or doing 1,2, which it never does. So 1,4 works. And we get a 1,4 addition product here with a new butyl here. 1, 2, 3, 4 on this carbon here. Now we're going to get good practice with the mechanism here. I want to finish strong though. So I think you're going to like what we're doing next. It kind of ties things together. We're going to get a lot of review in and throw the new stuff in at the end. So we're going to give a mechanism for all the reactions here. This is an aldol condensation. Do you know how I know that? The base will make an enolate here, and it's a simple aldol condensation. The enolate here is going to attack an unreacted version of this, which has 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and generate this here. So without much further ado, we'll start on the next page where we have a nice blank on the previous page. And assuming we're going to need red first, blue second. That's a dark blue. We don't use that one. And we have this H here. That's a lame attempt at an isopropyl. And what else can we short form here? I think that'll keep us going. Wow, that's a stray lone pair if I ever saw one. Okay, hydroxide, taking an alpha H. LDA. I got blue arrow. We don't do that. LDA takes alpha H. Don't have an alpha H. Alpha to 2 carbonyls. Definitely going to take that one. And OH minus AQ. Sadly, we got to redraw that. That's that saponification. Hydroxide. So a good tip to you, when you see me put OH minus AQ, I'm trying to guide your thinking towards saponification. Otherwise, I'll just have OH minus. And LDA is going to take this H here. This is a directed Claisen. See, there's a lot of chapter 19 stuff. Alpha H removal in every one except for this one. And down here, we're going to have to think a little bit. But, you know, time is of the essence. To make this ring size 6, where was the alpha carbon that lost an H? Well, it seems to me this carbon here has no alpha H's, and that's the one here. So that's my thinking, and that's why I'm taking that H there. The other H's do come off, but they don't lead to anything productive. We got to focus on the one that leads to something productive. So what we have here is this one. Oof. And it's going to react with an unreacted version of itself. That's 5 carbons. 2, 3, 4, 5. Should be 4. And we can combine a couple things here. If we remember that we also made water. And we have the attack. And then the protonation. And we make our aldol reaction product. And it needs to become the condensation product by removing a second alpha H from here. We generated hydroxide right here. We could put a plus sign with it. We don't need to. Grab the other alpha H. Sigma becomes pi. And hydroxide comes off. Catalyst a second time. And this one here. This anion is going to attack This here, which has lone pair, resonates back. Keep the green going here. So we've got this. Got a new bond. And it's to a carbonyl that no longer has its leaving group. And you think you're done on that one, and you are not. You generated a OET minus. Grabs that H. Yeah. Bite the bullet. How much time I got? It's getting tight. Got that bond to carbonyl with an IBU on it. So there we go. That's a minus. Oh, what happened? Random arrow here. And HCl is used to protonate that at the end. Directed Claisen condensation. One of our earlier items today. And down here, we're setting up for the old 1,4 addition. I told you you'd get an example. Would I lie to you? So we got a CO2 ET here, and a methyl, and a lone pair, and a minus carbonyl IBU. It is a leaving group that's a nucleophile that's also a leaving group, vice versa. It can add 1,2 or 1,4, but it prefers 1,4 because the product will be more stable. Can't combine this with 2 steps. You need the pi bond in here for the mechanism in the next step. So you can't combine it. There's no pi bond there. So you've got your blue piece down here. Methyl CO2 minus, CO2 ET, sorry. You got your new bond, pretty exciting. New bond's attached to a carbon that has a propyl on it. That's a butyl. No, it's propyl. And goes to a carbon that has an ethyl. Enolate. Where's it going to pick up a proton? It's going to pick up a proton from water. Where's the water come from? Step 1. Resonate. Protonate. So that right here was the 1,4 addition. You don't have to put that comment on there, but that's what that was. We have 10 minutes to finish this. I want to make sure we do the last part. I may just put saponification, acidification, decarboxylation here. Don't try that on the test. And if we have time, we'll do it, but I doubt we will. So saponification / acidification, I may have typos, and decarboxylation. You could add for the nation to make it sound more righteous, but you don't have acidification. That's not, well, I've had worse typos. And that's going to go there. I'll just put it right there. Over the arrow. I started it. I got 2/3 of the saponification. But right now I want to do this. It's an aldol condensation, by the way, but it has a guy's name on it. Wouldn't you know? It's always guys. Guys and their egos, right? We got the Robinson annulation. I like the second part of the name. Do not like a guy's name on either part of the name. It's just an intramolecular aldol. It's not even the first one we've seen. Some references call it a Robinson annulation. When you anneal things, you glue them together. That's a good name. Annulation I like better because it has a biological element. Trees, they make a ring every year. Annually, they make a new ring. We're making a ring here. We don't have to wait a year, but the idea of making a ring is the same. So we're generating an anion on the alpha position. That's the anion that gives a ring size of 6. Let me just run it down. If you chose this anion here, you would not make ring size 6 when you attack this carbonyl. It'd be ring size 4. That's alpha. It's potential that you could lose an H there, but it would be attacking that position over there, and the ring size would be 4. 1, 2, 3, 4. Similarly, alpha here attacking this carbonyl is ring size 4. 1, 2, 3, 4. But this anion attacking this carbon, ring size 6. Watch. 1, 2, 3, 4, 5, 6. We love ring size 6. There it is, ring size 6. And we'll just copy down everything we see there. Got an isopropyl down here, got an anion here, carbonyl, C with a methyl. If I swing the methyl to the left and the other group to the right, and put a propyl here, 2, 3, and then keep going to a carbon with an ethyl. And now we have the carbonyl in position to be attacked. And yes, that's an anion that's going to be attacking. And we also made water. And we have lone pair here. We attack, make lone pair there. Second step, the anionic oxygen protonates. And we make something that looks a lot like our final product, except it still has the alcohol on the beta position. And I'm going to copy that final product with the alcohol on the beta position. It looks like we did a rotation of about 30 degrees, huh? There's an OH here. There's an alpha H here. Needs to go away. We have that. And we're going to make that into our final product. Using base that we've been using all along, hydroxide. It got made right here again. It's been a catalyst all along. Grab the alpha H, sigma becomes pi, leaving group leaves, and there we have it. I will leave it up to you to do saponification, acidification, decarboxylation. We've only done the first part of the saponification, but I'm giving an Orgo 1 exam shortly, and you need time to start studying. Your problem set is almost ready. I'm maybe posting it tonight during the Orgo 1 exam. So that would give you an extra better part of a day to work on it. I'm not promising anything, but if I post it, I will send you an email as soon as I've posted it. And without further ado, I will be on my way and I will see you Monday. But you are studying full force now, aren't you?